Just a second. Okay, so I think we have solved this at least. Some others that are received privately. This is done. Okay, this is another problem. It's fine. Okay, so we are on the actual content now. So let me start from this last question that we got. So HMM, Kalman filters, particle filters, as I've mentioned in the video, they are not mandatory except HMMs. So on HMMs, I can spend a couple of words, extra words, but I think there is not a lot to say in the sense that on hidden Markov models, you apply exactly the same algorithms that we have seen. So the algorithms for filtering, prediction, and smoothing, except that the transition probabilities and the observation probabilities become just matrices. And so some computations are very easy to be performed. So actually, I have a Python notebook that is showing you an example of a filtering process on hidden Markov model and how you can implement a hidden Markov model very simply. So again, in the end, this is already a hidden Markov model because we have one single state, we have an observation, the state is unobserved, the observation is observed clearly, and the only thing that we did here differently is that we used the values manually. We went there and have been looking at the probabilities like if there was no matrix there, but in the end you can reduce all of this to a multiplication of matrices, and this is shown in this slide here. So I'm saying this is the computation that we did before. If you use the matrices, these matrices, in the end you can just do this thing here. So I don't know, if you're using MATLAB, for example, you just take your previous format message, multiply that by the transpose of the transition matrix, and you multiply finally by the pre-multiply by the observation matrix, and you normalize everything. Again, on Kalman filters and particle filters, I didn't want to spend a lot of words because you will see Kalman filters for sure in probabilistic robotics and in autonomous and mobile robotics. Particle filters, you'll see them in probabilistic robotics. So I don't think it's worth spending more time than this. I just wanted to mention that there is also this topic. Last year, I went more in detail on those. This year, I think it's not worth doing it because you'll see this anyway. Okay, so I hope this is clear now. We can get to this later. Let me jump to faster things first. HMMs, again, yes, they are mandatory. And let me be also clear on this. HMMs are mandatory for those of you who will not do the projects, because if you pass the exam with the projects will be about reinforcement learning only. So the probabilistic reasoning part is really for those of you who will take the oral exam. Okay, so other question that we got is, are the observations, which are component of the dynamic systems, random variables too? And the answer is yes, of course. This is why we are estimating the probability of. So if you go here, we are doing, for example, the computation of the probability of some observations given the state. Right, so these are evidence of some random variable which is determined by the observation function over the state. So again, if we go at the first slide here, we say that we have a transition function and an observation function. And this last observation function produces z, and I mean, given that the state is also a random variable, applying a function on a random variable will anyway result in very likely in a random variable. Okay, so this is how the thing is modeled. Okay, so. Now, we are going back to the forward and backward messages. Here. So the question was, can you re-explain how you're getting to the recursive estimation of the filtering function? So we say, let's assume that we have an estimation of the previous state. So that this is the assumption that you start working on. The assumption is, I have an estimation of my previous state. Now I want to compute what is the probability of my next state or current state. So can we do this? And the question is solved by looking at the definition of what we are trying to do. So we are trying to compute the probability of the next state or the current state given all the observations from the beginning until now. So this is the same as computing the probability of the current state given the observations by splitting basically these evidences in what I had until yesterday, what I have today. What is the current observation that I got today? Now, if we do this split, right, we get to have the following formula, which is the probability of the next observation, so the current observation, sorry, given the current state and all the previous observations multiplied by the probability of the current state given all the previous observations. Okay, so this last point here is useless because the observations we know are independent one from another. Okay, so we're saying that this is the same as computing the probability of the current observation given the current state multiplied by what we call the one-step prediction, which is the probability of the current state given all the previous observations. Okay, so what are we doing here in practice? We are saying, given the assumption that I know an estimate of my previous, or actually a prediction of my previous, of my current state, I can integrate this information by using the observation function. So this is O. The observation function is being applied here just to integrate the new observation information. So I'm plugging in my system this information about the last observation that I have received by assuming that I know something already about the current state. Now, is it true that I know something about the current state? Not yet. how can I know something about the current state? I can just take the previous state, multiply this by the transition function, and then I can get an estimate of what would be the current state. So this is how you do the one-step prediction. So again, let's say you have some information about your previous state, given all the observations until then you multiply this estimate by the transition function. So you are stepping forward one step in the state space. And then you're saying, I want to now make better this estimate by considering what I have observed today as well. And how do I do this? I take the observation function and I check what is the probability of getting that observation given my estimate. I plug this information there, and this is the overall computation that I need to do. If you have further questions or it's not been clear yet, you can, of course, ask questions again here on Slido. Actually, please, if something is not clear, do it here now. You can ask questions here. Okay, so slide at page 27, the third formula. Here. So the third formula, this is on the smoothing. So let's first then answer this other question, which is about the backward message, and then we'll go to the example. So the backward message. What are we trying? What is the goal of the smoothing process? You are trying to get a better estimate of some previous state given the observations that you got until now. Okay. So again, what I say in the slide, let's say we are at Sunday and we want to get some estimate about what was the rain state on Wednesday. So we want to compute the probability of rain at Wednesday, given that I have observed all the umbrella observations until Sunday. Okay, so why do you want to do something like this? Because by seeing what happens in the future, I can sort of improve my estimate of what was the previous state, right? Because if I know, for example, that there is a relation, right? Because there is a relation thanks to the transition matrix between yesterday and today on raining. If there is a higher probability of rain the day after today, then I know that my observation is more likely to be rain tomorrow instead of not rain. In my observation will be umbrella actually, but the state will be rain. So this is why we do this thing, to sort of improve our estimate. Now, how do we do it? Let's say we want to, our K is Wednesday. So we are estimating, again, our rain state until Wednesday. So from Monday to Wednesday, what we do is we do filtering. From Sunday to Wednesday, we need to do the backward message computation. How do we compute this backward message? Basically, we start by observing the we start by observing what was the value that we got as evidence. We plug this information in, and from this information we say, you know, very likely this was the state. Now I use the transition function to go backward. I use the transition function to go backward, and this will say, you know, this is probably what was yesterday then. And finally, I plug in again the previous observation. So I use the observation function, and in this observation function, I will basically, from this observation function, I will get some new information on how to improve my estimate from what I thought it was. Yes.
The more I go backwards, the more not great.
Of course, so the uncertainty increases the more you go backward, because of course you're doing a probabilistic estimation. So eventually everything will become flat if you go too many days back. So everything will be uncertain. When I say everything will become flat, I mean something like this. Let me draw. I need to stop sharing and I need to share something new. Share screen, whiteboard. So let's say this is Sunday, Saturday, Friday. Sorry, I don't have my pen today, so I'm just using the mouse. Thursday, Wednesday. So, and let's say we are computing our probabilities in the form of Gaussians. So we can say that by getting some observation on Sunday, we can estimate our state with a Gaussian, which is something like this. Then the more I go back, the more this Gaussian will become flat, right? So this will be, in the end, much more flat because my probabilities will spread out on all the possible states that we can have. So this is, of course, normal. You will see this a lot in probabilistic robotics. The classical example there is that you're trying to compute the probability of your robot being in a certain location given the observations that the robot had about the environment. And then, so you have basically probability distribution over all the possible locations to start, and then you plug in the observation information. And the more, if you do smoothing, the more you go back in time, the more you will see these probabilities being spread over all the possible locations. In this case, it's very simple. We're using Boolean states, so there is not a lot to spread, right? It's two values. Eventually, it becomes a uniform probability distribution. But and this is more clear and visible, I think, in the robotics localization example. Again, you'll see this a lot in probabilistic robotics. So going to the formulas, is this what is happening? Let's just look at the last formula for the computation of the backward message. So as I mentioned, we start from the last observation, we plug in the information from the observation function, okay? And then we say, okay, what is the probability that this was generating instead something in the future? So this is the recursive call. And we multiply the transition function. So this is our previous estimate, our future estimate. So this is the estimate from the future. And you plug in this information by multiplying your estimate by the transition function and by the observation function. So if you do this in the example, now we go to the question of your colleague, which was asking why. So in third formula, probability of U2 given R1 should be probability of U2 given R2. Given R1. Why would you think that's the case? It's not, right? So if you do this computation here, you're saying that the probability of R1 given you 1 and U2 is the same as the probability of R1 given you 1 multiplied by the probability of U2 given R1. So this is the filtering process. So this is the forward message, and this is the backward message. So you're saying the probability of the observation in the future given the current state. So the state that I'm trying to estimate. So this is, again, this is filtering. We are fine with that. And this is the backward message. The backward message, you're trying to compute the probability of the previous state given some future observation. So this corresponds, as you know, using bias and all of that, to trying to use some information about what is the probability that some observation is generated by this state. So then the other question that the student had was, why is it 0.9 and 0.2 instead of 0.9 and 0.1? Now, this is an answer that I have given a couple of times. Now, this is because the probability, so you need to look at this first row, first column of the conditional probability table. So you don't need to look at on the row, but you need to look on the column for this. So this is the probability of the observation being valued true, and then here you would have an extra column, probability of observation being false. Given that we know that the probability that the observation is true because we're using lowercase notation, so this is an evidence and this is true. Our evidence is true, and then we need to look at this column, and so this is why we're using 0.9 and 0.2. So these and these are Mark has answered. If you have more questions before we'll move to the Colab example, you can ask them now. Is there anything in class that is not clear? Kevin, you can keep sending questions if you have while we move on with this. Okay, so hidden Markov model, coding example. So what did we say? We said that we can model our hidden Markov models using matrices. So what are the matrices that we need to know? The transition matrix and the observation matrices. So the observation matrices are, you have one observation matrix for every value that the observation can have. So you will have one observation matrix for true and one observation matrix for false in this case, because we are dealing with a Boolean random variable. So looking at our example here, the probabilities are written here. It's a bit small. Maybe let me increase the zoom. So this is the transition function. So the probability of getting the next state true, given the fact that the previous state is true, is 0.7, and the probability of getting the next state true, given the previous state is false, is 0.3. So we are modeling this in our transition function, so 0.7, 0.3, and this is the probability of it being false. In this case, they correspond, so it's just a symmetric matrix, and that's it. In many cases, actually, you have situations like this where the transition function is a symmetric matrix. It doesn't have to be, though. There is no mandatory information on this. And then our observation matrices are 0.9, 0.2. We have seen this from the previous example. So this is the probability of the observation being true given state true, given state false. And this is the observation, probability of observation being false, given that the condition is true and given that the condition is false. Now, this and this need to sum to 1. This and this need to sum to 1, not this. Okay, so we're printing now our matrices. So this is 0.7, 0.3, 0.3, 0.7, and so on and so forth. Again, this is a diagonal matrix, the observation one. This is a diagonal matrix, so meaning that you have only the values in the diagonal of your matrix, and everywhere else you have zeros. Okay, so what can we do on this HMM? You can do exactly the things that we have discussed. For example, for bias networks, we can do direct prior sampling. And then on, let's say, we're using this to generate some trajectories, some events, some sequences of observations and states. Then what we'll do is assume that we only have the observations, we don't know what the state is, and we'll use, for example, filtering in order to compute the probability of the state. Okay, so for the direct prior sampling, what we're doing, we are generating 10 sequences of 8 days each. So of course, what I didn't mention is that you have a prior. This corresponds, your prior corresponds to R0. Is the S0, the state at day 0. So the one where you don't have any observation, because it's some prior information. This is something that doesn't really exist, right? It's something that you model in order to have some prior information and to start computing from there your filtering or prediction processes. So as we did last time, we're just looping here over the length of the events that we want to generate. We sample a random number. Then we say if this random number is smaller than the probability, we're saying smaller than the probability of the value being true, then you set it to true, otherwise you set it to false. Then you sample another random number because you want to sample what is the observation given the state. So according to which state you got, you sample. You look at the probability of the observation being generated true or not. And then we take this new state and new observation that we got, and we append them in our list. We keep generating until we reach the limit of 8. By keeping, of course, track of what was the previous state, and that's it. Okay. Of course, I will publish this notebook as usual. This will be published on Classroom. So if you don't have the time, or you're not familiar with these Python notations yet, you can look at those, get some more familiarity with it. I've been assuming that you all know Python, but I don't know whether this is true or not. If you don't, Python is a simple language anyway, and you will use this a lot in your master. So, one way or another, you need to learn that, not only for this part of the course, but for the whole machine learning course, and for the also for many other courses in practice in this master. So we generated a bunch of sequences of days. So we have our states and observations. States and observation. So let's look at one day. At one sequence, for example. We have rain being true for a bunch of days here at the beginning, then false for other 3 days, and again true. And our observations mostly correspond to this, in the sense that we have the same sequence of 3 false here and 2 true here. But sometimes the guy who enters with the umbrella in the room forgets the umbrella. So here, even if it's raining, the guy goes in the room without the umbrella. So now, let's say we only have this information. We are the person in the room, only observing this stuff, and we want to get some estimate of what is the estimate. Sorry, what is the state outside in the world. What do? We can do some. We can apply some filtering algorithm. So the one that we have seen. So day by day, we look at the guy entering the room, we mark this information in our computer, and then we integrate this information to get what is the probability that today is raining. So how do we do this? We let's say we are taking one single observation, the first one. So we are already in here now. So we start from our estimate being all zeros, and then we start by taking the observation and your previous estimate and multiplying this by the transition function transpose and the observation matrix. The observation matrix is the one that you choose based on the actual value of the observation. So given that you're seeing only the observation, if the guy enters with the umbrella, you choose all true. If the guy enters without an umbrella, you choose all false. Yeah? And then you normalize everything, and that's it. It's really simple. Now, sorry, I said I initialize my forward message with zeros. This is not true, of course. You initialize it with the prior, which is what I've been saying already before. So now, based on this observation, this is our estimate of the state. So this is the first row is the estimate for the state being true, and the second row is the estimate for the state being false. So we are correctly estimating most states. So true. I mean, here we're saying that it's more likely that it's false, just because we saw for one single day the person entering without an umbrella. Then we're saying true, false, 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 true, true. And as you see, here you have a higher probability of the state being true, just because from here to here we transitioned from a false to true state. So there is more uncertainty on the fact that it was raining. But now, if I was using a smoothing process, given that I see that the day before it was actually, the day after it was actually raining, I could have, had a higher value for this state here too, as well, to be true. So this is very simple in the end. Also, if you're doing the backward message, it's nothing really crazy, except that you're initializing your backward message with all ones. So this would be b equal a vector of dimension 2 composed of ones, and then you would iterate backward on the observation. So you would do from the last observation to the one that I'm interested in. So you're going backward. Here we're going forward. And then you would just do the computations in your that you have seen in the slide. So for the backward message, we are just doing, we're taking the previous backward message, multiplying this by the observation function, and multiplying this by the transition function. And then you would again normalize, and this would be your backward message. Finally, if you wanted to do the forward backward algorithm, you would multiply your forward message for a certain observation with your backward message for the same observation, and that would be the full smoothing thing. Is there any other question on this topic? If not, then we'll move ahead with the theory already today, given that tomorrow we have another class. And I want to recall that tomorrow afternoon we have another extra class from 4 to 6. So let me stop sharing. I'll prepare the slides set and we'll go through that. Okay, so today we'll start basically talking about one of the main ingredients for reinforcement learning. So the formalization that we'll use from now on for modeling our problems, which are Markov decision processes. Okay, so again, as you can imagine, the word Markov is because they are Markovian, as I've mentioned already. In Markov decision processes, you have a situation where your current state depends only on the previous state and not on the history of previous state. But we'll talk a bit more about this in the next slides. So reinforcement learning is based on the theory on the decision theory and on the theory of utility maximization. And when you're dealing with decision theory, the problem that you're trying to solve is choosing among different actions based on how desirable these are. And you can evaluate the desirability of an action given by some immediate outcome. This immediate outcome is typically called Now, what the agent, so the algorithm, is trying to really do is try overall, especially in reinforcement learning, when you're dealing with sequential problems. So you can deal with sequential problems or short-sighted problems where you only see one step at a time, and then you don't care about the next sequence of decisions that you take. But in general, you're trying to maximize the accumulation of these immediate outcomes that you get. So the cumulative reward will be the term that we use that the agent is collecting. You can deal with non-deterministic environments. Typically, the environments that you deal with are non-deterministic. Although some of them can be also deterministic, but that's not the typical case. In reinforcement learning, we deal with fully observable environments generally, but you can also have partially observable environments. What does it mean? Partially observable means that you don't see, or actually the agent does not see all the full state that it's dealing with. So I want to say one thing regarding this, which is the fact that you can have, even if the state is not fully observable for the agent, the environment is still Markovian in many cases, meaning that the actual state only depends on the full state. But there is a but in this. From the agent's perspective, the state is not Markovian because it does not see the full state. So if the state is not fully visible for the agent, the state might still be Markovian, but it's not Markovian for the agent. Okay? So if it starts seeing more things about the environment, then if it sees the full state, then it becomes Markovian also for the agent. But if it does not, then the agent will have a perception of a non-Markovian situation. And there are ways to try to make the observation more Markov. This is the typical wording that you will see. I want to make the observation more Markov for the agent in such a way that the agent can actually take rational decisions. Okay, so in general, in the decision theory, you have a certain outcome of a certain, beyond the reward, which is the number that gives expresses the desirability of a state. The outcome of a certain action beyond the reward is the new state, right? So what are we doing here is we are adding to our let me draw something here. Annotate. Okay. So we are adding something to our probabilistic temporal model, where, let's say, S prime. So this is how we are transitioning between states, right? So this is the transition function. And eventually, you can also have an observation function here. See? Eventually, because you don't see the color is not great. Let me maybe if I turn off the light. Is it better? Okay, sorry. So the observation function generally corresponds to just the identity. So you will see exactly the same state in a Markov decision process. But it might not be the case eventually. As I mentioned, you can have a partially observable environment. And this transition here is not only depending on the previous state now, but also on some action. So this is an action that has an effect on the transition. So your probability of next state is not anymore depending on the previous state alone, but also on the action. So the reward function expresses for the agent some information that is, again, the desirability of a certain state. But this depends on the preferences of the, what the agent is going to do not only depends on the immediate reward, but on the preferences that the agent has. These preferences are captured by a utility function, or what more generally in reinforcement learning we call value function. Okay, so I will use, in this set of slides, I will use interchangeably U and V to mention what is the utility function or value function. So U and V are the same thing. Okay, so U of S basically will represent how desirable a state is for the agent. Okay, what is the difference between the reward and the utility? So the utility is what is desirable from the agent's perspective. The reward is some immediate information that comes from the environment, so it's external to the algorithm or to the agent. And this also deserves some clarification, but let me first say this. It's external to the agent and comes from the environment, and it's something that says this state is good now. Doesn't express any future or personal agent information. Okay. Now, when I say that this utility, the reward is external to the agent, this is true partially. It's always external to the algorithm, but there are cases where the reward is defined by the agent itself, in the sense that it has some intrinsic, for example, motivation in doing something. So this intrinsic motivation can translates in the agent getting a personal reward in doing something. Okay. Overall, what the agent is trying to do is maximizing then the expected utility of a certain action given some evidence, which in this case corresponds to the state itself. Okay, I'm using the broader notation here to then go back to the more MDP Markov decision process one. Okay. So what is the expected utility then is just the average utility on the next state weighted by the probability of that state. Okay, so this is the expectation of the utility on the transition function, basically. Okay, so we are multiplying the expected utility. Expected utility is the same as the weighted sum of U on the next state multiplied by the transition function, which is, as we mentioned, depending on A. Now, the next state. So this is exactly what we said. We want to do argmax over the actions on the expected utility. So we want to maximize, we want to choose the action that maximizes our expected utility. And in practice, this thing is very, very hard to do, because first of all, you need to be able to get a good estimate of this utility, given you're not only observing it in expectation. And if you're dealing with a robot, you need to do perception, you need to do learning eventually, you need to use inference models and all of this. Now, there are a couple of slides here on the theory of utility theory, and I don't want you to go too much in details of this. I just have these slides here in order to give you some background if you want to understand what we're talking about more in detail, about what is a rational decision and so on and so forth. You don't have to. Okay, so everything that you need to know about these first slides here is that you have a different transition function that depends on the action, and that the agent is trying to maximize this utility or actually expected utility function when it's taking an action. And then also that by taking an action beyond getting a new state, you also get this some immediate information, which is the reward. Okay, that's everything I want you to know about this. So don't ask me, please, do we need to know this? Because the answer is no, you don't. So you need to know only what I spend time on. Though if I skip the slides, means don't spend too much time on it. What I want to say regarding this is that you can have different utilities. They don't have to be the same. Even for getting the same action, right? To choose the same action, you can have different utility functions. Because, for example, one might just be a linear transformation of the other. Okay, so the values might be actually different, but it's the same for the respective of the agent, because maximizing one or the other is the same. Also, the agent can typically have different kind of preferences, and this doesn't mean that the agent is being irrational. Actually, the thing is that the summary of the previous slides is that a rational agent is always maximizing some utility function that is well defined in terms of being a utility function. But if you take a well-defined utility function, you can have any kind of preference without being irrational, because it just depends on how your utility function is defined. Okay. Then here there is one example that you can look at home if you want regarding this. Something that I said want to spend time on is the fact that, again, we said the optimal agent, now we are adding this information, the optimal agent will take actions that are always maximizing the true expected utility, the true one. So let's say you know exactly what is the utility function, and in expectation what that is, the agent, the optimal agent, is always taking an optimal action, and this optimal action is computed as the argmax of this expected utility function. In real world, this is what I was mentioning before, is you don't work with the true expected utility function because you don't know that. No? You work with an approximation of it. You're trying to estimate that utility function. So this means that the agent, first of all, will not always take the true optimal action. So it will take an action which might be optimal to the current estimate, but which is not the true optimal action with respect to the true expected utility function. And that your approximation might be biased. So an unbiased estimation means that in expectation you don't have any difference between the approximated expected utility function and the true expected utility function. In practice, this is not true, and this is very hard to get. So we can look at one example where also, if you have an unbiased estimate, your outcome might be worse than what you would get if you had the true estimate, because we're saying that to be unbiased, the difference needs to be zero in expectation. So if the difference needs to be zero in expectation, your error can be zero mean, but can have still a standard deviation equal to 1. So let's say we have this situation. So your error has zero mean because the expectation means you are computing the error here. So this is the error between the approximated expected utility function, the true one, and we're saying the mean has to be 0. We're saying nothing else in the standard deviation. Now, if the standard deviation is 1, so this means that sometimes the error is positive, sometimes the error is negative. But this leads the agent to be anyway biased, because given we're doing an argmax here, we're always trying to get the highest estimate. So you will get the action that the agent will be taking will be still biased by this error. So the bias is clearly something that you don't want to have in this situation because it leads to something that is not correct, at least from the perspective of the true expected utility function. So the only point that I want you to know about this slide is the regret. What is the regret? So the regret is what you have when you give up some price for a higher probability of getting a better price, and then in the end you lose. Okay, why do I want you to know this? Because it's some information that you use a lot in machine learning in general and in imitation learning, which is related to reinforcement learning. So it's basically what you are losing because you were hoping on something better. Okay. So now this leads us to Markov decision processes, because we say that a rational agent is maximizing this utility function that generally we are working with expected utility functions that are approximated, and that now our transition function gives us some new state given an action in the previous state and some reward. This is exactly what you have in Markov decision processes, except that, as I mentioned, the transition model I mean, it's non-deterministic, that the transitions are Markovian, first order Markov, that the state is fully observable by the agent, and that this reward that we get can be greater or smaller than zero, but generally is bounded, so it will never be an infinite value or some big oscillation of values. You will have typically values that range between -1 and 1. This is the standard thing. You can have also larger rewards, but again, there will be a bound on the value that you can get. And the utility for a reinforcement learning agent, so the value for a reinforcement learning agent will be the sum of the received rewards, so the accumulation of the rewards. So the reinforcement learning agent wants to maximize, when taking an action, the sum of the rewards that it is receiving. So typically then we model a Markov decision process as a tuple composed by SATR, where S is the set of states that compose the Markov decision process. A is the set of actions that are available to the agent. T is the transition model, which is typically unknown by the agent. So the agent doesn't know the transition function. Okay? It's not known by the agent. Otherwise, the problem would become very simple. In reinforcement learning, the transition function is unknown. We'll see now some examples where the transition function is known, and you can see how you can compute the optimal action in that case. But if you know the transition function, you're typically doing planning, you're not doing learning. Okay? You're typically doing planning on a model where you know on an MDP where you know the transition function. Or eventually what you can also do is trying to learn the transition function. Then you would do planning for the part where you use the learn transition function, and then you do learning for the transition function itself. For the reward function, you will see many notations. So you will see that the reward function can be a function of S, can be a function of S prime, can be a function of S and A, can be a function of S and A and S prime. So several combinations of this. And in the end, what you need to know is that for a single transition, so a transition, for a single transition, you get one single reward, and a transition is the following thing. Annotate. Okay. Use the text here. So the transition is something where you are starting from a state, you take an action, and you end up with a new state and that's right, and a reward, and there is something else. In many cases, not always, but you will see this, a termination flag. termination, sorry, not capital, lowercase t. This termination flag will tell to the agent whether the process has stopped. So if you reach a terminal state, then you can't do anything from there. You cannot do anything there. So most MDPs have a terminal state. Not every MDP has a terminal state. This is why it's not included in this initial notation. Okay. So as we mentioned, the MDP has fully observable states. The transition model is Markovian, and the rewards are additive. In the case where you don't have a fully observable MDP, and you call this POMDP, which is partially observable Markov decision process, will not touch them a lot in this course. Maybe a couple of slides about those, but not really. But you need to know that they exist and that they are difficult to deal with. So that's why you always try to make your state from the agent perspective again fully observable and in order to deal with MDPs itself. This is not the anymore because so this is the typical then of an agent interacting with the certain environment. Yeah, somebody has turned on the microphone, and there is. I can mute the person. No, maybe it's already done. Okay. So the agent interacts with the environment by taking actions. That's everything that the agent does. It observes the state of the world and takes some action. And that's everything that happens from the agent's perspective. It gets some rewards, of course, but then it's the environment that gives the new state, it gives the reward to the agent. Again, the reward can be something internal to the agent, but we call this agent meaning the algorithm. So the algorithm the algorithm receives the reward, and that's it. Okay. So as we did for our temporal models that we have seen last lesson, we interact with the environment at discrete time steps. So we're discretizing the time, basically. And by interacting with the environment, the agent generates some trajectories of states, actions, and rewards, and eventually termination flags. Okay, so this S0, A0 are 1, S1 is for us one transition. Then the next transition will be S1, A1, R2, S2. So as you see, there is some S1 belongs both to the first and to the second transition. So if you're storing your transitions in the form of trajectories, you need to keep this into account, because it means that you always have one state more compared to the rewards that you get. Sorry. Yeah, so in a finite MDP, you typically have states that state actions and rewards that have a finite number of elements, and both R and S have a discrete probability distribution only depending on the previous S and A. So it doesn't have to be discrete, but can be continuous as well. So this is one example of how you can model an MDP in the form of a graph. So these are the states, right, where that the agent can, that the environment can have. The actions that are available to the agent are search and wait when the state is high, and search wait a recharge when the state is low. Something I didn't mention that is that the action set can change depending on the state. So in some states, you might not be able to perform some actions. For example, in this case, when the state is high for the charge level, then you don't want to recharge. So it's not part of the action set. So the agent cannot choose that action. So then there are some probabilities of transitioning from one state to another by taking some action. And there are some probabilities of getting, there are some reward values that you can get from these transitions. So as we mentioned in the reinforcement learning case, and in general, when dealing with Markov decision processes, even if you're not doing learning, but you're doing planning, the goal is that of maximizing the total amount of reward that the agent receives. So we're not talking about the immediate reward alone. So we don't care a lot about the fact that the agent is receiving plus 100 now, but we care about the fact that instead of receiving only plus 100 now and zeros everywhere else, we want to receive plus 1 for 1,000 steps, for example, which is better for the agent's perspective. So the expected value here is the expectation of the cumulative sum of the rewards. So the example that I gave also implies that the agent might give up some immediate high reward in order to get a longer term accumulation of reward, which is higher than the immediate one. Okay, so the agent doesn't have to be short-sighted, but the agent has to be considering in the long term the consequences of the decisions that it's taking. So how do we compute the expected value here? So the utility function or the value for us, again, is the accumulation of the rewards, the sum of the rewards, which we call a return. So we want to, the return is typically represented by this letter G, so which is the accumulation of the rewards again, where until t, where t is the final time step, so where the termination flag is true, then that's the final time step. And typically you are trying to compute the expectation of this return and maximize this expectation of the return. So in the expectation, we want to maximize the return, but not necessarily in every single trajectory that the agent is taking. Again, in computing the return, we are considering the whole trajectory that the agent has generated in the environment, and we are taking all the rewards that we got, we sum them, and this gives us a notion of the return. Okay. So yeah, if we have a final time step, then we're dealing with so-called episodic tasks, and we want to generally deal with episodic tasks because if the tasks are non-episodic, meaning that they are continuing tasks, then the return is just infinite, right? So there is no limit to the value that you can get if you keep summing rewards. In order to deal with this, you typically introduce a gamma value, which is called a discount factor, which is basically telling the agent, so this value is between 0 and 1, and it's basically telling the agent whether it has to be short-sighted or not. So if gamma is 1, then you're in the case where you're taking all the rewards and you're considering the same, all of them the same for the agent. If gamma is 0.99, which is a common value for gamma, then you're giving a lot of importance to the feature, but not, I mean, you can be also a bit more short-sighted, which is also useful in the case when you have infinite or actually continuing tasks, because otherwise your return sums to infinity. You don't want to do that. And if gamma is 0, then it means that you are only trying to get the maximum immediate reward, right? Because then this will become RT plus 0 times RT plus 1 time plus 0 times, which all of this becomes 0. So your return is composed by RT plus 1. So you're trying, when taking an action, the agent is just trying to maximize in expectation the immediate reward. Okay. So let's look at one example. This will be our first Markov decision process, where we have this transition function. So if you take a certain action of going left, up, or right, in any case, you will end up in the correct state. So left, up, or right will probably 0.8, and in the wrong one will probably 0.1. Okay. So we're considering a grid in this case. So the set of states for us is the locations of the grid. Those are the states that we are dealing with. The actions are these three actions that are up, right, and left from the agent perspective. And the agent always receives 0 reward except in this terminal state and in this terminal state. So these are both terminal states where it receives +1 and -1. Again, this is a MDP, so everything is observable. Actually, I say the reward that the agent gets is -0, but in practice it's -0.4 in this example. Sorry. So we can compute, for example, here the probability of getting up or getting in the goal by following this sequence of actions by just doing this computation, which is 0.8 elevated by 5. Why? Because if you take an action, the probability of ending up in the correct state is 0.8. So if I take up, I will end up in here with probability 0.8. If I take up, I will end up here with probability 0.8. If I take right, I will end up here with probability 0.8. And I will end up instead here in this other state with probability 0.1. Is it clear? I see you're confused. So for every action in this Markov decision process, if you take an action, the probability of ending up in the next state that you were trying to get to is 0.8. With probability 0.1, you're ending up in a different state next to that. Okay. So in order to compute the probability of reaching the goal state here, you just need to take 0.8 and multiply that 5 times, which is the number of times you take an action. So if the agent gets in this state, then the utility that the agent has, setting gamma to 1, is just if you do this in 10 steps, then the utility will be 0.6 because it will be 1 plus minus 0.04 multiplied by 10. Okay. Okay, now that we have an MDP, we know that the agent is trying to maximize some utility function that is defined in terms of a sum of rewards with gamma or without gamma, depending on the task, whether it's, how the MDP is defined. What does it mean to find a solution to an MDP? Finding a solution to an MDP means to find a policy that is optimal. Now, a policy, let's say first, what is a policy? A policy is a mapping from states to actions. So it's a mapping for all the states to actions. So when sometimes I ask this question at the exam, which is, let me go to the previous slide. If this is the MDP, how do I notate this again? Drop. Okay. So if this is my MDP, is this is this a policy? What is the answer to this question? What do you think is the answer to this question for the people in class at least? It's not a policy. Why? Because this is a mapping only for these states to an action. It's not a mapping for all the states to an action. So it's not a policy. Okay. So given a certain policy, you can measure the quality of this policy by looking at the value function, so at the expected utility. So as I mentioned here in the slide, the quality of a certain policy pi, which is pi is simply the notation that we use for the policy, or you can see that interchangeably we will use action sampled from P of A given S, or the same will be pi of S, like if pi is the probability. Okay, this to say that pi typically is a stochastic function. It's not a deterministic function in many cases. In several cases, it's stochastic. It can be deterministic sometimes, but not so often. Anyway, so how do we measure the quality of a certain policy pi? We do it by looking at the expected utility of the histories, so the trajectories generated by the policy itself. So an optimal policy is the policy that always brings the agent to the highest expected utility. So now, why is this the case? Why do we have this action in this case here for the optimal policy? What do you think is the reason for this? I mean, you could say from 1 tree it should go up, right? Why it's not the best thing to do? Simple, right? Because the transition function eventually, even if it is unknown to the agent, sometimes brings the agent from this state here, brings the agent in here. Right? So you don't want to grow in this state because it's a state where you might fall in -1. So if you fall in -1, in the end, you are getting a worst, on average, you're getting a worst return, expected return from here going up, rather than just doing this full loop in order to go to +1, because this is safer. It's more safe to do this. Huh? Okay, yeah, this is what I was mentioning. Okay, so we say that if you don't have a terminal state, then you have infinite trajectories and you'll have infinite returns if you don't use the discount factor, which is gamma. Okay. When you have infinite sequences, you try to make them finite by using gamma smaller than 1, and you use bounded rewards. So basically, this will help you in getting a correct estimation of your utility function, as this will be how you can conclude that. Okay. Then instead, if the environment contains a terminal state, then a policy, will reach a terminal state, and you can use just additive rewards without using a discount factor. Although sometimes you still, often you still use a discount factor even in episodic tasks. Okay, so we say the case of additive rewards is the case where basically gamma is 1. We can always say that gamma is here, except that in additive rewards, gamma is 1 always, and in discount rewards, gamma is typically smaller than 1 and higher than 0. we already say that if gamma is close to 0, the agent is giving importance only to the immediate reward. If gamma is 1, then you are in the same case of additive reward. So how do we compute a policy? Right? We say that the solution to an MDP is a policy, and we want to compute a policy. How do we do this? In order to compute a policy, we need to estimate our utility for a certain policy. Sorry, we need to compute our utility, which is a sum of discounted rewards, as we already said, that are obtained by starting from a certain state and then following a certain policy. So let's say you start with a random policy. Okay, random policy means I take always random actions. I take these random actions until I reach a certain terminal state, or until I fix a certain number of steps that I can execute my policy for. And then I evaluate my policy based on the utility function. So I compute the utility function by looking at the trajectories that the policy has generated, collecting all the rewards, summing them, and doing basically the mean, the average in expectation, seeing how in expectation these returns are, and giving a value for this policy. Then I can compare in this way two policies, and also I can compute a new policy based on the value that I just got of the previous one. How? We'll just see in a few slides or tomorrow, depending on the time. I mean, maybe we'll be in time to do it today. Anyway, in order, let's say instead you have the utility function already computed for you, then the policy will be just the argmax of the utility function for all the states. Okay. So the policy that has the highest expected utility is the optimal policy, and the optimal policy will also be evaluated in an optimal value function. So if you compute the value of an optimal policy, that would be the optimal value function. Okay, so you can also compute a policy if you have the utility function in the following way, by doing the argmax over the expectation of the utility function, but this requires you to know the transition function itself, which you don't know. So the question is then, given that we don't know the value, so we say we can compute the utility or the value if we know a policy, and we can compute a policy if we know the utility. So it's like a dog that is trying to get to his tail. So how do we do this? Because we don't have any of those. It's a problem, right? It was probably unclear when I was explaining this. Why do you say that you can compute a policy from the utility, and you're saying that the utility can be computed from a policy? We don't know how to do any of these things. So there are ways to do this by using the two algorithms that are called value iteration and policy iteration. In these two algorithms that are planning algorithms, we will assume to know the transition function, because we'll see that then algorithms that are used when you don't know the transition function basically behave in a similar way. They just get rid of that assumption. So in the value iteration, the idea is to the one of calculating the value for each state, and then use this value to select what is the optimal action. Instead, in policy iteration, you evaluate. You start with a policy, you evaluate your policy, and you try to improve your policy step by step. Okay, so in one case, you compute the utilities and you use them to compute your policy. In the other one, you use directly a policy. So you start from a policy and you try to optimize your policy. So for all of these algorithms to be understood, you need to understand what is a Bellman equation. So the Bellman equation, I assume you have seen that already in some courses like ricerca operativa, operational research. Typically, you see this in this kind of course. If you didn't, we'll see this anyway here because it's the basis for almost every reinforcement learning algorithm. Okay? So the Bellman equation is defining the utility of a certain state, the value of a certain state, based on the utility of neighboring states. So we are saying that the utility of a certain state is the reward that you get in that state plus the maximum, right, of the utilities that you get in the neighboring states multiplied by the probability of ending up in that neighboring state, right? So here we're using the transition function. This is where we're using the transition function, maximizing this utility function that you can get from the net states. So let's say that I know how to take an optimal action in the next states. Then everything that I need to do is look at my utility function, see what is the best action from the next state, and then take that action in the next state and just get the reward that I get in this state here. So I can maximize and I can compute this utility function again by just looking at the reward that I get in this state and maximize from now on the utility function from the neighboring states. So this is known as the Bellman equation, and here we have one example of computing this. So what is the utility of the state 1, 1? This will be the reward that we got in this state, which is minus 0.04, plus gamma, the discount factor, and we do the maximum over all these situations where we can end up with. So with probability 0.8, we can end up in 1, 2 if we go up. We can go with probability 0.1 in 2, 1, with probability 0.1 within 1, 1, we can stay, right? Because if you don't, so what I didn't say before is that if you have a wall on your right and you try to go right, you will stay in the same state. Okay, so this is how these MDPs define. So if you go left, you will have probability 0.9 of staying in 1, 1, right? Because it's 0.8. If you go left, you will stay here, plus 0.1 of staying again here, plus 0.1 probability of going in 1, 2. And you can do the same for all the actions, and then you take the maximum one. So assuming that you know the values of these other states. So you take the maximum of all of this. So we are doing the sum over all the possible actions. So we are considering all the possible scenarios that can come up in our future. We are plugging them together by using the probability of those, and then we're computing our utility. So if you have n possible states, then you have n Bellman equations, because you can have this same equation for all these states, right? So we have, let's say we have 12 states, except that this is not a real state because you cannot end up here. So it's 11 states. Then you have exactly 11 equations of this kind, and each of these depends on the other, because we are computing the utility of 1, 1 based on the utility of 1, 2. And in 1, 2, in the equation of 1, 2, you will have again the utility of 1, 1 being used. And not only this, these equations are also non-linear. Why? Because we're using the maximum operator. So this is hard to solve. And you can do it, however, by using iterative approaches. And this is exactly the case of value iteration of the value iteration algorithm. So in the value iteration algorithm, you start with some arbitrary initial value for your utility. Typically, you can start with 0. So you set utility of every state to 0. And then until we reach equilibrium. What does it mean we reach equilibrium? The values don't change anymore. So for each state, simultaneously, or one after the other in practice, you do exactly this computation here that we did here, assuming that the value of u1, 2, for example, is the one that you have set at the beginning. So 0. We start with 0. So basically, at the first iteration of value iteration, the value of 1, 1 will be minus 0.04 only. Same for this one, same for this one. Only here we'll get minus 1 and plus 1. At the next step, now every of these individual states has some value. So here now we have minus 0.04, and 1, 2 will be minus 0.04 as well. So eventually you will be propagating this information from here to here to all the states, and there will be a certain point where there will be no update anymore because you have computed the exact values. Okay. So there is a guarantee that you will be reaching an equilibrium, and that this will be a solution to all of your equations. And this is a unique solution which corresponds to also to the optimal policy, which means that if you take an action by maximizing this utility function computed by the value iteration algorithm, then you are obtaining an optimal policy. Okay. So there is the pseudocode for this. I mean, that the explanation is exactly what I've given to you. Again, this is here we're using notation U. This is the same as using V. It's the same utility, value function for us are the same thing. Can we look also at policy iteration? Yes. So for policy iteration, we proceed in a different way. So what we did in value iteration is we said there are values for every state. We try to compute these values, and from this we compute the policy. Now we'll do a different thing. We start with the policy. From this we will compute the utility, and using this utility we will try to compute a new policy. So, and this algorithm will iterate until the policy, until the utility again will not change anymore. Okay. So you start with a policy. Again, this policy can be random at the beginning. So given the policy, now you can compute the utility, because we say that we look at the. Let's go to the slide. So we can compute the utility of a certain policy. Right, we can do this, and this step is called policy evaluation. Okay, so we take a policy, we compute its value, and we do policy evaluation. While actually in practice you prefer to do policy evaluation because it's easier to be done. So you evaluate your policy by just taking the action. So you sum the reward again to the utility of the state that you would end up with in a probabilistic sense, of course, by taking the action that the policy gives you. Now, instead of considering all the actions, you consider one single action, which is the action that the policy gives you. So you see the difference from what we did before. Here, we considered all the actions. We are taking the maximum over all the actions. Here, we're considering one single action. So the action that the policy would give you. So now this equation is linear because you don't have any more a maximum operator. You have n states, n linear equations, n unknowns. You can find a solution to it. And how can you do this? You compute the value of your policy, and then based on the value of this policy, you will compute your new policy by taking always the argmax of the value that you computed. So if the values don't change anymore, then you're done. Otherwise, you can keep iterating on this. So many reinforcement learning algorithms are organized in these two steps. So here, just to repeat it, we are doing planning, right? We're doing planning because we're using the transition function. We know it. We're doing planning. We're using the transition function. We consider all the possible states that we end up in. In reinforcement learning, this information is not available. You don't know in which states you can end up in. You just experience that by interacting with the world. So you need to collect this kind of information. You don't have a model that says this to you. Still, many algorithms are organized in reinforcement learning. Many algorithms are organized in the way of having a policy evaluation and a policy improvement set. Okay, so in the policy evaluation, you have a policy. Again, you start random. You compute the value of your policy without knowing the transition function. In that case, you try to estimate that, and then you take a policy improvement step based on the value that you compute. And I would say that at this point we can pause here and we can resume tomorrow from moving from planning to actual reinforcement learning, because now we introduced all the concepts that we need. Just to recap, we said what a utility function is, which translates in a value function for us. That in reinforcement learning and in general, when you're dealing with Markov decision processes, even in planning like value iteration and policy iteration, you are computing the value as the expected utility of, as the expectation of the sum of the rewards discounted or not discounted according to the scenario that you're dealing with, and that an agent tries to maximize this value in order to behave in a rational manner, and eventually, if the agent is capable of computing the optimal value, then it should be able to compute also the optimal policy, and also that an optimal policy translates in an optimal value function when you compute one from the other. We have seen two algorithms that allow us to compute the value of the value and a policy, one from the other. So value iteration and policy iteration when you know the transition function. Now we'll start getting rid of one of these pieces, which is the transition function. We don't know that. We'll remove this and we'll switch to reinforcement learning. Okay, so this will be what we'll talk about tomorrow. Let me just see whether there are any questions on Slido here. So no, so the one question is why 8 elevated by 5 when it goes right, the probability is not 0.1. No, that's the notation that was used in this slide here is if you do the correct action. So even if you're going right, you will end up right with probability 0.8, up with probability 0.1, down with probability 0.1. So this is what these slides mean. It's not up, right, left. This is if you take an action, you end up in the true state, in the state that you wanted to end up with probability 0.8, and otherwise in another state with probability 0.1. The class tomorrow will be in room B2 as usual. And the other thing is, I didn't understand what is the reward function. And again, the reward function is an immediate signal that the environment gives to the agent. It's something external to the algorithm, something that is defined in the environment, let's say. So it's something that is part of the Markov decision process. It's not, it's something given, let's say. It's something that is given to you, and you need to create an agent that maximizes the value being computed as the expectation of the returns, where the returns are the sum of the discounted sum of the rewards. Okay, so this is the summary. I think this is quite clear at the moment. If you have other questions, we can address them tomorrow. So that's it for today, and